Dear students, welcome and thank you for tuning into this video. We are going to be presenting another biomedical instrumentation lecture, and I will be talking about the classifications of biomedical instruments, as well as medical research studies and static versus dynamic characteristics of biomedical instrumentation. We will start with the classification of biomedical instruments. This is a very important topic for all biomedical engineers, where they need to understand what kind of classes of biomedical instruments do we have. And we have multiple ways in order to do this classification. You can classify the biomedical instrument through their quantity that they are measuring. You can find biomedical engineering instruments that actually measure pressure, flow, or temperature. And you can say that you would like to be specialized in all the biomedical instruments that measure pressure, or the ones that they measure temperature. So you can categorize the biomedical instruments through the quantity they measure, or you can categorize them by the principle of transduction. Remember from the previous lectures and videos, we said that the most important component or part of a biomedical instrument biomedical engineers need to pay attention to are the sensors and the microcontrollers. Transducers are the devices that they will be converting one form of energy to another form of energy. You can be specialized actually in biomedical instruments that use resistive properties as the principle of transduction. And we're going to talk about them in the following videos. Or it could be inductive or capacitive. For example, a capacitor, we have two plates, and if you move the distances between the two, the one plate away from the other, capacitance value and the voltage will change, and that can be actually a transducer. Or ultrasonic or electrochemical. So this is another way in which we can actually classify biomedical instruments. So the first one was quantities, the second one was principle of transduction, and we want to learn more about it. You can also categorize biomedical instruments by the organ system that this device or instrument is designed for. So you can say, well, I want to specialize in the cardiovascular biomedical instruments, or the pulmonary, nervous, or the endocrine systems. So you can select one of these organ systems, and you can say that you would like to specialize in all the medical instruments that are used in diagnosis and treatment of this particular organ in the body. Or you can actually categorize biomedical instruments based on the clinical medicine specialties. For example, you can say, well, I would like to learn and to design biomedical instruments that are used in pediatrics or cardiology or radiation. So this is a very important slide that shows you the different classifications of biomedical instruments based on different classifications. And I keep saying to all biomedical engineers that in order to be successful in this wide spectrum of opportunities in medicine, find a medical problem that you'd like to solve, and then learn everything, all the technologies that can be used to solve that medical problem. And that's why I am one of the guys who like the clinical medicine specialties specification for biomedical instruments. I would like to touch base on some biostatistics and the applications of statistics in medical data, because there are a lot of reasons why we need to look at statistics rather than absolute values in medicine. And especially for biomedical engineers who are going to be designing and developing biomedical instruments that can measure the biological data. As a biomedical engineer, you can work actually, if you spend time and effort in learning biostatistics, which I encourage all biomedical engineers to do. You can design experiment and clinical studies. You can summarize, explore, analyze, and present data. You can draw inferences from data by estimation of the hypothesis testing, and you can evaluate diagnostic procedures. And also you can assess clinical decision making. And that's a very important actually field or career pathway for biomedical engineers. Remember, biomedical engineering is a research-based discipline, and we would like from all our engineers to be able to do this and do some research and discovery and involve in advanced studies and publications and clinical trials and clinical studies. The reason why I'm showing this is that I feel it's very important for all biomedical engineers who are interested in instrumentation to keep biostatistics and research in their mind when they think about career pathways. Now, what is medical research, and do we have different types of studies, or do we have classical studies that we do in the medical field? So we have two different types of studies that I would like to touch base and explain for you. The first type is called observational studies. And these studies, we have a couple of types of these studies. So you can have something called case series studies, where we have a question that people would like to identify, or a symptom, or an observation that is presented in front of a physician. He or she wants to do case studies. So it's series studies are on individual subjects. We don't have control. We just want to study and observe what is the medical condition and its symptoms and what could cause it, and that's to identify questions for further analysis and research. We can have something called case control studies, where we can find a specific group of people who share, let's say, symptoms of a specific kind or a medical condition, and we look back for causes or risks that could have created this specific medical condition. And we called case control studies because we have a group of people and we try to go back to the causes or the risks. We can have something called cross-sectional studies, where we can analyze at one time point to determine status of disease. So you can say, well, for a specific group of people at the age of 30, we would like to find out a specific or measure a specific parameter. So that's called cross-sectional studies. And then we have something called cohort studies. And cohort study is that we know that there's some group of people who were exposed to a specific agent or condition, and we want to monitor them over time and to look back at what happened, what kind of risks factors they actually could have had to cause this medical condition. So all of these observational studies, actually, they are not controlled, and they are not large scale. They are not multi-center studies, and they all depend on the observation of a physician or a group of physicians for one person or one subject or a group of subjects, a small group of subjects. Now, what I want you to look at is something called experimental intervention studies, and those are the ones that we actually want to focus on because we can get more reliable data from these. So what we have is if you do anything that is related to medical, you need to do experimental studies, and then you need to do clinical studies. And what we mean by experimental studies means that you are going to be testing your drug or intervention or medical intervention on let's say non-human cells, small rodents like mice and rats. You would like to test on pigs and dogs or monkeys. So that's all experimental. And once you do your test on humans or human cells, that's considered clinical studies. So experimental interventions, they could be experimental studies or clinical studies. So if we said we want to study effect of one drug on people, we can do controlled clinical trials, and what means that you need to take a group of people, split it in half, and then give half of them the drug, and the other half does not receive the drug. So and we monitor the parameters that we would like, the clinical parameters that we would like to study, and that's called controlled because you have one group that took the drug and another group that did not take the drug, and that's called concurrent as well. Now, we have something called uncontrolled clinical trials, where you have only one group that receives only the drug, and you don't have a control group that does not receive the drug. And we need to make sure that when we say controlled and uncontrolled, or a group that receives the drug and the other group does not receive the drug, if a subject knows that he is receiving a drug, there is a psychological effect that can affect the biology and the clinical outcomes of the result of the study. So that's why we came up with something called double-blinded controlled clinical studies, where you have a group of people, you split them in half. Half of them will receive the drug, but the other half will receive placebo. Let's say something that's fake. It's not the drug, but it could be saline or water. But we put them under the impression that they receive the drug to remove the bias from the psychological effect. And that's called blinded controlled study. Now, in these blinded controlled studies, the physicians or someone who is doing the experiment will probably know who received the drug. And that could create bias actually in looking at the data and inferring what the data is telling us. That's why we created something called double-blinded randomized control, studies, which means double-blinded means that the patient does not know, also the physicians does not know, or the one who is conducting the research does not know. So they do the randomization of the patients and randomization of who received the drug and who received the placebo. And this is the best way actually in doing clinical research. So that's the double-blinded because the physician does not know the patient as well. And randomize that, we do randomization of who is receiving the drug and these studies, and that minimize investigator and patient bias. And then we have another type of studies that we have multi-centers, double-blinded randomized controlled studies that we do on a larger scale, like what happened when we had the COVID-19 pandemic. So I wanted you as biomedical engineers, before we get into the biomedical instrumentation in more depth, I wanted you to know that once you design or develop your instrument or medical intervention, we need to be able to do these medical research studies to prove the safety, short-term safety, the efficacy, and the long-term safety of your medical device or medical intervention. And keep in mind, research and discovery is something that is really a good pathway for biomedical engineers. I would like to talk about some biostatistical parameters that we will be using over and over when we study, anything that is related to biomedical instrumentation and clinical research. So we have key measures, and we call them descriptive statistics. That we probably know about those, and you're probably taking, or took statistics class. So we have something called the mean, which is an indication of the center of the values. That's the average, and we call this as moment, right? So we have mean-based measures and we have non-mean-based measures. So if we want to look at the center of your value, you can use the mean, which is the average, or you can use the mode, and the mode is the most frequently used value in your observations, and the median is the value that splits your observations in half, 50-50. That's median. So you can use the mean, or you can use the mode or the median to identify the center of your observations or readings. Now we can look at the spread actually of the values or the readings or the observations, because that's another important aspect in statistics. And we can quantify spread by doing something called the variance or the standard deviation. That's a mean-based measure, and we're going to talk about it a little bit more in a bit. And we have a non-mean-based measure that is the range, or something that called the interquartile range. I don't know if you remember the box plots. So the box plots splits your values actually in 4 quadrants. So that's the Q1, Q2, and Q3. And the data that are between Q2 and Q3 is actually what we call the interquartile range. And remember, we'd like to have, if we're doing observations, if they're accurate, we would like to have them as normal distributed as possible. And remember, in the box plot, this point here is the median of your readings. So the interquartile range is between these 2 lines, this line here and this line there, which is Q2 and between Q2 and Q3. So that's non-mean based measure that's related to the median as well. And the range is the between the minimum and the maximum values. That's the range. So all of these variance range and interquartile range are an indication or a measure quantification of the spread. Now also we are looking at the skew of the data, and that's another important measure. How the data is skewed. Are they skewed away to the left or to the right of the mean of your measurements or the average? And we can look at also something called the keratosis, and that's another important statistical measure for the data, and what it means is the sharpness of the peak of a frequency distribution curve. And I'm going to show you a couple of these, you know, quantities and how do we measure them, and show you some kind of schematics representation of those. Now, for the mean, we all know that the mean is the average, so the summation of all observations or readings or measures divided by the number, and that's the mean, and that's how we actually represent it. Now, for the variance and the standard deviation, it's actually how distributed or the values are away from the mean. So you can have something called the variance, which is sigma square, which is the the difference between the values and the mean square, the summation of these values divided by the number of readings. And if you took the square root of the variance, you get the standard deviation. And that's an indication of how spread the data is. So the higher the standard deviation, the larger the spread, the smaller the standard deviation, the smaller the spread of the data. And that's something that's important because we don't want to have a lot of outliers in our data. So if you have outliers in your measurements, it means that you have a larger standard deviation. And that's something we try to avoid. You need to understand that. The normal distribution example. So this is a normally distributed, frequency distribution of readings. And if we have something like this, that's normally distributed like a bell shape, that's good. That's very important. That's very good. And there are a lot of quantities in actually around us that are normally distributed. For example, the IQ, the intelligence, measure of people, so that's normally distributed. So we have a mean value, and then people are distributed around it. You can look at the SAT results for people, for the population, height of people. This is an example of the height. So 70 inches is let's say the mean, and people are distributed equally on both sides, lower and higher. And so this is a normal distribution example, a bell-shaped distribution. We don't have skewness, so we don't have any, tilting toward the right or the left of the mean value. We have all we can call zero skew, symmetric, and the mean and the median and the mode are the same value here. So that's an important statistical distribution that we see repeating itself over and over in nature. Now, if we want to talk about skewness, so it's an asymmetrical distribution, and for example, income is not symmetrically distributed. The contribution of candidates to let's say the presidential candidates for elections, population of countries. You can have countries with a large population and countries with low population, and depending on the resources. And so there are a lot of examples. So this one here, the one that we're looking at, is positively skewed or right skewed. So if you can see, this is the mean value from the normal distribution, and then you can see that they are skewed to the right of that mean, and that's called right skew. We can have another skewness that is called, left skewed. So the GPA of the MIT students, they're high achieving students, so their grades are high. That's called negative skew or left skew, to from the mean around it, and that's another representation that we would like to for you as biomedical engineers to know that these are actually things that we can see if we study biological parameters or biological phenomena. Now, regarding the keratosis, we have as I told you, it's a measure of the flatness of the tip of the distribution. So you can have something like this. So if you say that we have meso keratotic, that's Latin, which means that it's in the middle and the intermediate, and that's given a K value of 3. If we have something called leptokeratotic, and that means small or narrow tip of the distribution, and that K value is larger than 3, and if the K value is less than 3, that platykeratotic, which means big and wide flatness of the tip of the distribution. So that's another thing that we will probably see if you do research in the clinical, study clinical data and do research in healthcare. Now, normal distribution, the characteristics of the normal distribution. As I mentioned before, we have zero skewness and kurtosis of 3, and that's something that we actually would like to see in our data, but that's not the case all the time. So this is a quick representation of some of the biostatistical parameters that they are actually important for us to consider when we study biomedical instrumentation and we do design development and we do clinical trials to test our medical devices. Remember, medical devices, they can't be sold in the market without having the approval of the Food and Drug Administration. And that approval is actually depending on it depends on the data that you present that prove the safety, efficacy, short-term safety, efficacy, and long-term safety. And in order to demonstrate that, you need to do studies and you need to present your data, do statistical analysis for your data for the FDA to approve selling your biomedical instruments in the market. Now, what I wanted to talk to you about now is something related to the devices themselves when we design them. So I'm presenting an introduction before we get into the more detailed description of biomedical instruments. So what I want to talk to you about now is the difference between static and dynamic characteristics of biomedical instruments and biomedical instrumentation. What we want to do, so there are a lot of medical instruments in the market, so you can find a lot of blood glucose level testing instruments. They have different types, different models, and different manufacturers. So how can you compare between those instruments, and how can you evaluate this instrument if it's working properly or not? In order to do this, we need to look at the static and dynamic characteristics of each instrument, and that's something very important for biomedical engineers to be able to compare and evaluate using the static and dynamic characteristics, and you can find those when you buy a new instrument, a medical instrument. There are a lot of documentation that comes with it that should have actually information about that. So what we want to do from how do we want to use these characteristics is to compare and evaluate the performance of instruments. These are quantitative criteria for the performance of the instrument. So that's something that we need to be able to assess and understand. And I'm going to present to you a couple of these characteristics that a number of these characteristics that you need to be aware of before we get into the design and development of biomedical instruments. So we have two types of characteristics, or two classes, and they are based on the frequency of the input, the thing that we are trying to measure. So if it's static, it means it's a DC, there's low variation or zero frequency. On dynamic characteristics, if you are the input signal has high frequency. For example, the ECG, the heart, the biopotential of the heart, that has a frequency. It repeats itself, right? The EMG, that has a frequency. It keeps repeating. We have a signal with a frequency that changes its value. So those are we need to look at the dynamic characteristics for them. If you're looking at something that is static, that is flat or does not change with time, for example, human temperature, the body temperature, that's a static. We look at the static characteristics of that device that measure the temperature. So to do so, static characteristics describe the performance of instruments for a DC or a very low frequency input, like the body temperature. And dynamic characteristics requires the use of differential and or integral equations to describe the quality of the measurements, because the frequency continuously change. Now I have a couple of examples for you, about what are those characteristics. So I will start with the static characteristics of a biomedical instrumentation. So if you have a medical instrument, you want to see if this is the thing that you would like to buy, and if you saw two, let's say, blood glucose measurement instruments, and one of them is very expensive and one of them is cheaper. So what are why the one is expensive and the other is cheap? So all depends on the characteristics, their characteristics. So for static characteristics, we have desirable characteristics and we have undesirable characteristics. For the desirable characteristics, for example, in a medical device, you would like to have accuracy, right? And it's expressed as the percentage of the full scale of the values which is the measured minus the actual divided by actual multiplied by 100%. So that's an accuracy that you would like to see in all biomedical devices that they need to report. And we're going to talk a little bit more about it. Then you have something called the sensitivity here, and is the smallest detectable change in the measured quantity that produces a perceptual change in the instrument decision. And it's a measure of the ability of the instrument to detect small changes in the measured quantity. So that's something good. You want to have high sensitivity for your instrument. Also, we have something called the static error here, and it is the difference between the true value of the quantity being measured and the value indicated by the instrument. And this error is actually caused by the inaccuracy of the instrument itself and does not change over time. So it's just static. It's just the same error over and over and over again. And the ways that we correct for this is through calibration. So we can account for this through the calibration, and that's a procedure that biomedical engineers do all the time in hospitals, where your job as a clinical engineer is to do preventive maintenance and calibration of the biomedical instruments in the hospital to make sure that they're giving you the right data. Then we have something called, so we're going to talk about all of these in a bit, most of them in a bit, regarding biomedical instruments. Now, for the ones that they are undesirable, we have something called drift. Drift is the change in the reading of an instrument over time due a variety of factors such as temperature, humidity, power, fluctuation, and aging of the component. And this is an undesirable, actually, outcome of a biomedical instrument. We need to minimize this. And this drift can be caused by this can cause the instrument to give inaccurate reading over time and must be corrected or compensated for to ensure accurate results. And that also can be done using actually calibration. Now we have something called hysteresis. And hysteresis is the lag in the response of an instrument when the direction of the input or the stimulus is changed. So if you're reading positive values and then suddenly you're reading negative values, there is going to be a hysteresis, which is a lag in the response of the instrument because of this sudden change in direction or of the measurement. That's something that we measure. And so, for example, when a thermometer is exposed to an increasing temperature, the temperature reading on the thermometer will lag behind the actual temperature if you change it to low temperatures, right? This is the hysteresis of the measurement that we're looking at. And then we have something called dead zone, and that's another thing that it's undesirable in the medical instruments. And the dead zone is the range of values that the instrument cannot detect. And it is typically a low amplitude range in which the instrument sensitivity is not sufficient to detect a signal or make a meaningful measurement for us. So those are the things that you would like to look for when you buy a medical instrument, or when you design a medical instrument. You need to report those, and you need to report for the Food and Drug Administration. And those are the things that actually affect the price tag for your instrument that you're presenting. So those are static characteristics. Again, static means that the input is DC, zero frequency, or very low frequency changing. Sorry. Now what we want to do is to go into the dynamic characteristics, and we have desirable and undesirable. And when you say dynamic characteristics, is that when the instrument is measuring something that has high frequency or changes with time quickly. So the desirable is we want to have a high speed of response for the changes, and we want to have something called fidelity. And fidelity is the degree of exactness with which something is copied or reproduced. So reproducibility is fidelity. Sorry. Now, undesirable value, characteristics is dynamic error and the lag. And we talked about the dynamic error, and that's an error that exists actually because of the device itself. just similar to the static error, but now it's dynamic and it depends on the frequencies of the quantity that we are measuring. Now, lag is the period of time between one event and another, and that's another thing that is undesirable actually when we have dynamic, for as a dynamic characteristics for the device. Let me show you a quick example actually here. So we have something called one of the static characteristics that we mentioned before is accuracy, and it's the difference between the true value and the measured value divided by the true value, and then you multiply by 100% to get a percentage. Now we have two types of accuracies, two ways to represent accuracy. It's a measure of the total error without regard of the type or source of the error, and that's why we like it, because it's a collective measure of errors. And we have two ways that we can represent it. We can represent this as a percentage of the span gauge or percentage of the reading gauge. And when I say span gauge, will mean the entire range of reading. So you can put your device on two modes. So you can say that I'm going to be measuring an entire range. For example, this is the pressure, and I can measure from 0 to 100 psi. If you use that setup for your device, you will have a collective error of 0.1%, or an accuracy of 0.1%. And that's so that when you look at this here, the span gauge, the entire range of readings. So your error over the entire range of reading, if you set the device to do this for you, to have on that setup, you'll have 0.1 percent of reading. Now, if your device is set it up in such a way that it has ranges of values to read from, so we can say if you're reading from 0 to 20 psi, you will be having 0.02% accuracy. So that's accurate. But if you increase it to between 50 and 100, and you're getting 100, in that range, a different range, you get a larger, error, and you have the accuracy is different. The one that you're looking at. So that's important to look at. So it can be expressed as percentage of reading or a percentage of full scale. And you need to look at that into your medical devices when you buy them or when you report that we design them. So that's the accuracy of reading or accuracy of full scale. And it's usually the accuracy of full scale give you just one number for the entire scale, and you just report that in your readings. And that's something to keep in mind. And often expressed as a sum of these two. So you'll have 0.01 of reading, that's on the specific range, and of full scale 0.015 of full scale. So that's something to look at when you try to compare between two different medical instruments, and see the performance of these medical instruments. You want to make sure that that value, the percentage error, is as small as possible for you, and that means that it's a good instrument, and that's going to be an expensive instrument. Now we have something else called another static characteristic called precision, and the precision is of a measurement expressed the number of distinguishable alternatives from which a given result is selected. So for example, 2.434 volt is more precise than 2.43. So we have more precision here, right? We have more precision here, but that does not mean that it is more high accuracy. It's precise. So the device is precise because it can give you more numbers to compare, and that's a precise measure. But it does not mean that high precision does not mean that's high accuracy if the device is actually faulty. It's not going to give you what you want to. And you can look at this example here, or a picture of a caliber, and you can see that these small bars here those are the ones that can give you the precision of it, and that's how many digits you can have, let's say, after the decimal. So that's a good indication of precision. So if the smaller that you have here of these values are, the more precise actually the measurement is. Also, we can have there's another static characteristic called resolution, and it is the smallest increment quantity that can be measured with certainty, and expressed as the degree to which nearly equal values of a quantity can be discriminated. And that's, if you look here at the resolution, the smallest, the tiniest measure that you can distinct in your naked eye, that is going to be your resolution. That's how you look at it. Now we have another static characteristics called reproducibility, and it's the ability of an instrument to give the same output for equal inputs applied over some period of time. And reproducibility is really important in healthcare, even though that it's really achievable, because we are dealing with the human body, and we have a nonlinear biological system that is affected by a lot of factors: environmental, biological, chemical, and even psychological and emotional. So reproducibility is a big challenge, and that's why we would like to do statistical analysis for reproducibility. Now keep in mind, on a funny note, that a broken stopped clock is right twice a day. So you need to make sure that you are actually, when you do look at the data, that it does make sense for you and why you're using it. Now, one of the most important things that we would like you to keep in mind, at the end of this lecture and video, is something called statistical control. And as I mentioned before, we are dealing with the human body, and biomedical engineering is, related to medical devices or anything that is interacting with the biological living system, right? And our biological living systems are really complicated, and we cannot actually reproduce things 100%. That's why we're looking at something called statistical control. So the accuracy of an instrument is not meaningful unless, if we are designing an instrument, instruments are, linear systems, and their accuracy, they're not meaningful unless all factors are considered: environment, method of use, psychology, whatever the thing that's affecting the human body. We need to make sure that they all factors are considered, and we cannot replicate everything all the time. So we need to have something called statistical control to ensure that random variation in measured quantities are tolerable, and we have systemic errors or biases that can be removed by calibration and correction factors, as I mentioned before, static errors and dynamic errors. And but keep in mind, the human body is a complicated system, and that is why we need to keep in mind that in the case of variation, because if the cause of variability cannot be eliminated, then statistical analysis must be used to determine error variations. And that is why we actually studying statistical analysis and focusing on it when we look at biomedical instrumentation, because the human body is a nonlinear dynamic system that changes with time, and depending on a lot of variables. So we need to rely, if you want to quantify any biological quantity, you need to make sure that you are actually accounting using, for variation using statistical control, and try to eliminate, if the variability can't be eliminated, you need to use statistical analysis all the time to validate whatever you are actually claiming. So hopefully this lecture was helpful in getting us a little bit more into what are the important things when we study biomedical instrumentation. Thank you for watching, and until the next video. Bye.